But at that point, he's got some stupid speed going upwards, right? So he'll still, under projectile motion, keep going, right? If you've ever played with rockets, you know that the engine burns for a little bit, right? It doesn't start falling back down once the rocket turns off. It shoots up into the sky a little bit further before gravity has its way and makes it come back to Earth, right? So I want to neglect the second part. I want to neglect the projectile motion just to keep this example shorter. So what's the final velocity? Acceleration was what? 156.9 meters per second squared. The change in time. Now, 1 minute would be foolish here. What's the change in time? 60 seconds. Very good.
Are you also assuming that the 10,000 newtons are exactly over a 1 minute span?
Right. I'm assuming it is a constant thrust of 10,000 newtons over 1 minute. You could, in principle, think about all kinds of complicated functions of time and variable force. Then you'd have to do calculus. But here we have a constant acceleration, so we can go back to our constant acceleration formulas. Can you guys tell me what this is? What's the final velocity? Say again? 9,414. That's yeah, the cat is dead already. The cat can't take, I mean, unless this is a covered couch and it's got like, you know, better aerodynamics than like an SR-71, it's not likely the cat's alive at this point. It's also not likely you can find a couch that has the structural integrity to mount those rockets. There's lots of problems with this example, really. I'm sorry, I'll have to think harder about my real-life examples of cats and rockets. Next time I do it, it'll be more realistic. But we have the timeless equation to figure out how high it went, right? I mean, we could do that. There's other ways, I suppose, but this is just what popped in my head. So to calculate how high it goes, change in y is just what? It's vf squared divided by 2a. Remember, v naught's 0. So what's that? That's 9,414 meters per second. You square that thing. And we divide by 2 times the acceleration, which was 156.9 meters per second squared. And that will give me how high? How high is that? $282,000 what? 400 and what? 420 meters. So yeah, okay. So about 282.4 kilometers high. Not too shabby. Yeah, that's up there. I'm pretty sure that F equals mg is not quite good anymore. I think we're starting to get outside the range of applicability of that formula. We're starting to get where we need to probably start thinking about this one. But that's a little bit later in the course.
I'm under the impression this whole structure went disintegrated by now.
Yeah. So, and then even so, that's not the max height. So what we have is that is 282.4 kilometers. At the ending point, it's still got an upwards velocity of its VF is actually V naught for the next leg of its journey, which is projectile motion, right? So it actually keeps going even further up before it finally comes back down. So we've neglected that part of it in terms of its absolute total height. All right. So, you know, this concept of force, we will spend a lot of time thinking about force this semester. Yep.
Could you use, do you have to use a timeless equation, or could you use...
Have to use a what equation?
You have to use a timeless equation?
Oh, no, there's 3 or 4 different ways to solve this problem. We could just use, we got time, so we could...
Could you just do 1/2 acceleration?
Yeah, that's what I should have done. That'd been easier. Although it was nice because I found out the speed also, which is interesting. But yeah, if we were just after the position, that would have been a faster route. Now, the gentleman said some things about leptons and other things. I'd like to take a few minutes to talk about the bigger picture of physics and what we're doing. So Thursday, I will give you more examples of forces, how we solve force problems, all right? So Thursday, we'll do force problems. Who knows? Thursday, I may even have time to take a few web-assigned questions. We shall see. But right now, I'd just like to, for the remainder of class, talk to you about the big picture of physics. What's physics about? What's the idea of physics? And these so-called four forces. So the four forces, well, it's kind of funny because not exactly forces. So roughly speaking, you've got gravity, yeah. You have the, let's see here, electricity. So electromagnetic, we could say. Yeah, and then down here we got the, let's say, the weak force. And then over here we have the nuclear force. So these are the four forces. In about well, let's see here. I guess first of all, if you were around before 1860, you would have said there were five forces, maybe. Well, not really. 1860, these weren't so clear. You might have said that there were three forces. There's gravity, there's electric forces, and there's magnetic forces. So one of the first unifications that I think is interesting is around the middle of the 19th century, Maxwell came up with Maxwell's equations, which said that electric and magnetic forces were really just different aspects of one single concept called the electromagnetic force. So that was settled more or less around 1860. Gravity, there's different kinds of gravity to think about. There's Newtonian gravity, which is the kind we study in here mostly. So that was that Newton's universal law of gravitation, this GMM over r squared formula. That has quote unquote spooky action at a distance because it doesn't really tell you how gravity gets from where it's going to where it's acting on. There's no sense of like how long it takes for gravity to get from point A to point B. It just is. So Newtonian gravity really is best suited to describe static situations where the gravitational whatever is just kind of is what it is. Gravity waves, on the other hand, are something that would be described by something much more recently found, which is called general relativity. Now, general relativity is also known as GR. This was around 1916 to 1926, somewhere in there. This was Einstein's big, really big discovery. And so we're pretty sure that general relativity, at least something like general relativity, is reality, or close to reality. There's still open questions in general relativity. There's all kinds of things we haven't solved yet. One of the predictions of general relativity is gravity waves. So if you have something like a, I don't know, neutron star, and suppose it slams into a black hole, then basically it should send out ripples, these gravity waves, right? And if there's big enough stuff, well, you've been at a family reunion or something. You know, if a certain uncle jumps in the pool, you notice, right? So kind of like that. So every family has one, and you know, so I don't think, as far as I know, we haven't observed gravity waves yet. They're pretty hard to observe, but that's one prediction, general relativity, gravity waves. Another prediction is the precession of the perihelion of Mercury. Bending of light around stars. These things have been observed. Also, there's a correction to GPS that's general relativistic in nature. The other thing Einstein did was he did something called special relativity. I don't know where to put special relativity on this picture. I don't know where to put classical mechanics on this picture. All right, those are, well, I'm not sure how to fit that in here. Electromagnetic is what it sounds like. Electricity, magnetism. Some of you have chosen the study of this as your major. You're electrical engineers. This is your home. What's that? Yeah, okay. Now, nuclear force is what it sounds like. It's the force that describes how the nucleus is bound together. It's a little bit more than that. So you have the study of protons and neutrons, how they interact, how they glue together. We think that protons and neutrons are forms of things called quarks. The quarks are somehow grouped together in bound states in such a way that they assemble through the rules of representation theory, mathematics, to form protons and neutrons of particular shapes and sizes. Now, some of those are unstable, so they can change from one kind of elementary particle to another. That is governed by something called the weak force. The weak force describes radioactive decay, the tendency that certain matter has to decay from one form to another. For example, if you leave a neutron out on its own, like that, for too long, all of a sudden, it will become a proton. And then there will be an electron going that way, something like that. So a neutron, a free neutron, has a lifespan, a pretty long lifespan, about 11 minutes. It will spontaneously decay into a proton and an electron. And something called an electron neutrino, which is more ghostly and weird, and something we are only starting to really understand. Mr. Omby has been part of experiments which have helped us get closer to understanding neutrino physics. That's pretty cutting edge stuff. I don't know what our current state of knowledge is on that. It's complicated. All of this together is, roughly speaking, what's called the standard model. Around 1970, Glasgow, Weinberg, and some other dude, they found a way to put this and this together in terms of something called electroweak theory. Electroweak theory is the gauge theory of SU2 cross U1. It's like, in the same way that electromagnetism can be understood to be a gauge theory which is built over a circle, this can be understood, these collectively can be understood to be a gauge theory which is built over a more interesting looking matrix group. One part of that is there's this electroweak symmetry breaking, and in the process of symmetry breaking you have something called a Wino and a Bino, and what is it, the W and plus and minus and W0, and something else I forget the name of. Yeah, these bosons, they drop and they become the W plus minus and Z naught bosons, as well as the photon. In the process of the symmetry breaking, the weak force carriers pick up mass, and the electromagnetism, the photon stays massless. And that's why electromagnetism has a very long range, whereas the weak force has a very short range because its force carriers are massive. And that's been, very interesting recently. This Higgs particle, which is part of that story, has recently been observed in the last couple of years by the Large Hadron Collider over at CERN. So I don't know. This story is ongoing, and I'm out of time. So that's all in test.